All right, so chapter 4, section 1 of calculus. Getting into integrals now, which is awesome. So let's just do the order. They're going to introduce the integral. Well, I guess they're not talking about integrals yet. They're talking about antiderivatives. So antiderivative is the opposite of the derivative. So I guess they are talking about integrals here. But let's just read the question. Find the general solution of the differential equation. So they're saying that this is the derivative. See how they say y prime equals 2. The derivative is 2. So they're asking what equation has that derivative. And well, there's not even necessarily a strategy to that. You just kind of think about it. What equation is going to have that derivative? It's going to be y equals 2x, right? Because when you take the derivative of that, the x just goes away. And so it's just 2. So that's the general solution of the differential equation. Now, one big thing with integrals, which is just annoying more than anything, but does matter in particular problems, is that the only equation that has the derivative of 2? It's not, right? There's actually infinite of them. Because what if the original equation was 2x plus 2? When you took the derivative of that, the plus 2 is just going to go away, right? Or if it was plus 1, or if it was plus 22, or if it was plus or minus anything, when you take the derivative, it just goes away. So to account for that, when we talk about general solutions, we put a plus c there, where c is just any real number. C is just any constant. That's why we use plus c, because it's a constant. And we just put that there to show that there could be any number added or subtracted there. We have no way of knowing. But we do know the 2x part. So that's why we call that the general solution, because from there, maybe we can find the particular solution if they gave us a point that was actually on the graph. But without that, we can't get that. So that's just the general solution. Or that's the integral of 2 with respect to x. And so let's do another one. You see here, we're just doing it again. So describe the antiderivatives of 3x. So see, that's why it's antiderivatives, because with the plus c, there's always lots and lots of them. But think about, so what function would you take the derivative to get 3x? Well, if you think about the power rule, you know that it would have had to be x squared, right? Because if you do the power rule, you're going to decrease the power by 1 to get x. So the original function definitely had to be an x squared. But we need to, when we take the derivative, we just have to get a 3 in front. But think about how when you take the power rule, you're going to end up bringing that power to the front and multiplying by it. So we have to make that 2 go away. So that just means for the original function, we have to have an over 2 here. That way when we take the derivative, the 2 will cancel out. But then we are also supposed to have that 3 there. So then we also have to have the 3. So that means this is our original function. Because see how when we take the derivative, when we do power rule, the power would come to the front, just like on the right over here, and the 2's would cancel, and so you'll be right there with the 3x. And of course, like we said before, it has multiple antiderivatives because we have the plus c, because it could be plus or minus any number right there. So that's very fun. I mean, I don't know if they necessarily want us to. It looks like they do going into the next one. Let's write out a formula for this. So if we have... Well, I'll ignore the number, because the number just sits there, just like with limits and derivatives, same with integrals. So if we have x to the n, and we want to take the antiderivative of it, well, what do we do? So notice what we did here. We started with x to the 1. We realized that when we did power rule, we would subtract the exponent by 1. So that meant when we were reversing the power rule, you're going to have to add 1 to the exponent. And then normally in power rule, we multiply by the original exponent. So here we're going to have to divide by the new exponent. And then, of course, have the plus c, but that's just always there. So when you look at this, just kind of take a second and look at it and think about when you do power rule, what's going to happen? You're going to bring the power to the front, so the n plus 1 is going to cancel. You're going to subtract the exponent by 1, so the new exponent is just going to be x to the n. So this right here is our general reverse power rule. It's just the opposite of the normal power rule. And so that's basically what we're going to be doing with these. We're going to be seeing that we can rewrite that as x to the sum power, and then using the reverse power rule. So we're going to add 1 to the exponent and then divide by the new exponent. And you can take a second, pause, and just look. If you take the derivative of that using the normal power rule, you get back to what you originally started with, which is what we want to happen. And then, of course, plus c. And then the last thing you might just want to do is rewrite it more how it looked before. So negative 1 over 2x squared plus c. It's just the opposite of the power rule, just as easy as the normal power rule. So same here. You recognize that this is x to the 1/2. So you're going to increase the power by 1. So x to the 3/2. And then divide by that new power. Divide by 3/2. And so, of course, when you divide by a fraction, you flip it. So this ends up being 2x to the 3/2 over 3. And then if you want to simplify that x to the 3/2, that's just x root x. Because, of course, that's x to the 1.5. So it's x to the 1 times x to the 0.5. And there we go. Next, so this isn't the power rule, but we just got to think, what has the derivative of cosine, or the derivative of sine? What function do we take the derivative of and get sine? And well, it's definitely cosine, right? Except when we take the derivative of cosine, we get negative sine. But here we're taking the derivative and we're getting a positive sine. So doesn't that mean this is already negative? Because if you take the derivative of negative cosine, you'll get negative sine, which is positive sine again. So that's going to have to be a negative cosine. And then the 2 just has to be there as well, actually. So this is going to be negative 2 cosine of x. And of course, plus c on that one, and also plus c on that one. And let's just look for a second to make sure. So when we take the derivative of cosine, we're going to get negative sine of x. And we're going to multiply that by negative 2. So indeed, the negatives cancel to become positive, and we get that it's 2 sine x. And so, of course, when you're taking integrals, that's always how you can check your answer, is you can take the derivative of what you get, and you should end up with what you had originally. All right, very nice. So we're doing a few more. Oh, that's wonky, ain't it? But remember, that just means there's a 1 there. And so we're saying, what equation do you take the derivative of and get 1? Well, x. Just plain x, right? Take the derivative of x, you're just going to get 1. The derivative of y equals x is just 1. The slope of y equals x is just 1. So, let me rewrite that because it looks like a y. But you just get x. And the reason you know it's x is because it's dx. If that was like a dy or a dt, you would say it was t. But because that's telling you what variable you're taking the integral with respect to. It's just like taking the derivative with respect to a variable. So here's a rule with integrals, same with derivatives, is that if you're adding multiple things inside of an integral, you can always split it up. So this is going to be just like the integral of x and the integral of 2. It does not work when you're multiplying. Don't make that mistake. But just like with derivatives, if you're taking the derivative of 2 things added together, you just take the derivative of them separately. If you're taking the integral of 2 things added together, you just integrate them separately. If you're taking the derivative or integral of things multiplied together, it's more complicated. Because that's when like the product rule comes into play. So we're just going to take the derivative of both of these. So, it's power rule. This is x to the first right now, so it's reverse power rule. So it's x to the 2 divided by the new power. And then just like the one above, it was 1, so the integral was just 1x. This is the integral of 2, so the integral is just 2x plus c. And you could take a second, check, make sure if you take the derivative of that, you do indeed get x plus 2. And remember, that's the whole point of dividing by this, is so that the power cancels out when you do the power rule. All right, same thing here. You're going to take the integral of each of them separately, so each of them is going to just be a power rule. So this is increase the power by 1, divide by the new power. Coefficient stays. And then the coefficient stays, increase the power by 1, divide by the new power. And no coefficient, but it would stay. And increase the power by 1. Of course, this is x to the 1, so when we increase it, it'll be x to the 2. And then divide by the new power. And then, of course, plus c. So see, this is just reverse power rule. It's nothing that complicated. Now here, this might look complicated, but remember all the fancy stuff you did with power rule back in the day, before you even knew quotient rule and stuff? So we're going to do similar ideas here, even though we're not taking the derivative, we're taking the integral. But notice how when you split this up, so then you get x over root x plus 1 over root x. These are just x to some powers if you simplify them. So here, here you could rationalize to see it. I prefer to realize that x is the square root of x times the square root of x. So we can just cancel out one of those square roots of x's. So this is x to the 1/2 power plus x to the negative 1/2 power. And now if we want to integrate them, so remember, just like when we took the derivatives, we might do a whole mess. We haven't taken the derivative yet now. Now we're going to take the derivative. Now we're ready to not take the derivative. We're going to take the integral now. Now that we've messed everything up, messed around with everything, now we're ready to take the integral. So we're going to do the same. It's the reverse power rule because we're taking the integral. So we're going to add 1 to the exponent, divide by the new exponent. I'm going to go right to it and say when I divide by 3/2, that's going to be 2/3. And I'm going to do the same with the other one. I'm going to increase the exponent by 1 and then divide by 1/2. You divide by 1/2, that's multiplying by 2. And there's your integral right there. That's the integral of that. Maybe you want to make it slightly better. You really can't make it that much better, though. The fractionness of it kind of does go away because all the negative exponents of it go away. But anyway, we could rewrite it as like 2, again, x to the 3/2 is x root x plus 2 root x. That one's over 3, so if you wanted to common denominator and actually write it in one fraction, you can just do that. And of course, plus c. So I don't know, both of those ways are nice to write it. All right, I think we got a few more. So here is again just kind of messing around with stuff, right? Or not. Is this harder? Well, let's see. So what is, it's definitely trig, so we've definitely got to think about that more. We already did one trig though, but what can we do? So we've got sine over cosine. So maybe let's split this up to be sine. I don't know how stingy y'all are going to be about writing of x. Sine of x divided by cosine of x times cosine of x, which is what? So you have sine over cosine. So what is that? That's tangent. And then you have 1 over cosine. What's 1 over cosine? 1 over cosine is secant. So what we're left with is secant x times tangent x. So we're trying to take the integral of secant x times tangent x. Now, why does that help, you may ask? But now if we think, what can we take the integral of and get secant x times tangent x? That's just secant, isn't it? Yeah. The integral, the derivative of secant is secant tan. So if we take the integral of secant tan, that's just going to be a plain secant. Secant plus c. Secant of x plus c. And there we go. If we take the derivative of secant x is just secant x tan x, and then we rewrite it. So yeah. So they're just like, this is where your algebra skills come in. You've got to be able to schmooty stuff around properly to get to right answers and get to things that work for you. So like this, you just got to schmooty it until you get that's equal to secant x times tangent x. And you know if the derivative is secant x times tangent x, that the original function's got to be secant. All right, same idea. Find the general solution where the derivative is 1 over x squared. So This is really exactly the same as the other one. We're just doing the integral of x to the negative 2 dx. So we're just going to use the reverse power rule. Increase the power by 1, divide by the new power. So it's negative 1 over x. And of course, plus c. All right. So, yeah, that was an easy one. This one we got to work for a little bit because it's a word problem. So we got to think. So you might know some of these equations from physics, but we're going to basically derive those equations for now. So a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Find the position function giving the height s as a function of time t. Find the position function. Okay. So how do we do this? Well, let's say we don't really know any equations. We do know what is acting on this ball. We know that the acceleration, right? We know the acceleration no matter what. The acceleration no matter what is negative, we're in feet, so negative 33 feet per second. Right? We just always have to know that. But now that we've used integrals, we can think about how we said that the derivative of velocity is the acceleration. The integral of acceleration is velocity. So now we can integrate this bottom equation with respect to time, since that's the variable we care about. And what do we get when we do that? We get negative 33t plus c. Remember the plus c. But this is where the plus c matters, because now we can actually calculate the plus c. Because what do they tell us? They tell us that the initial velocity is 64 feet per second. So initial, that's at the beginning, right? That's when time equals 0. So if we plug in t equals 0 into this equation here, then we can calculate what c has to be. So we do that over here. We go v of 0 equals negative 33 times 0 plus c. But they tell us right here that v of 0 is 64. So that means that c has to be 64. So that's actually what our velocity equation is here. It's negative 33t plus 64. Since they gave us that one value that we knew, we could find our c. And then now let's keep going, because we know that the derivative of the position function is the velocity function. So if we take the integral of the velocity function, we'll get the position function. Well, so look here now that you've got to use the reverse power rule. So we're going to increase the power by 1 to make it t squared. And then we're going to divide this by 2. And here, this is just 64, so ends up being 64t. So see, that's just reverse power rule type stuff. And then plus c. But just like before, they tell us the initial position. They tell us the initial height is 80. So we can use the same type of thing and say that when time equals 0, the position needs to be 80. But when we plug in 0 for time, all the other parts just go away. You just end up with c. So that doesn't always work out like that, where c is just the initial condition. But in this case, it did. And there we go. Now we have find the position function giving the height s as a function of time. So they just wrote an s here instead of an x. But that's our position function. So now, when does the ball hit the ground? Well, we know the ball's going to hit the ground. What's the height when the ball hits the ground? 0, right? So that's what we're going to do, is we're going to set that equation equal to 0. And I really don't think they want you to use like your head here. I think they just want you to plug this in and solve for it. So let's go to Classic Numworks. Let's solve it. This is one problem I have with the equations. I always, there we go, have trouble clearing equations, I was going to say. So what do I want? Actually, yeah, see, I do want to clear that equation. And then I want to add equation, and I want to add that equation. It's nice to start with a template, so then I just come in here and do this, I guess. I guess I just need to multiply by 0.5 then to not slam it into a fraction. And then plus 64, and then plus 80. And there's our equation. Look at it again and make sure you typed it in right. And solve the equation. And there's our two answers. So you're seeing we get a negative answer and a positive answer. And that's just because we started up in the air. So, of course, if you think about what this graph looks like, it's a parabola. So we're starting like somewhere here, roughly. So they're saying if you imagined going backwards, that would be 1 at roughly -1. And then forwards would be 1 at 4.873. And of course, we're not actually going backwards in time. So we just want the one where it goes forwards. And that's pretty cool. I mean, that's a great little application of the integral, is deriving these physics formulas. See how that's a physics formula you should know, that it's the acceleration over 2 times t squared. And see, that's why it's over 2, because of the reverse power rule and the integral. And then the v naught t, and then the initial height. Like, that's a physics formula you should know, but we can derive it using integrals, starting from the constant acceleration and integraling down until we get the position. So that's very nice. That's basically, I mean, I say as I look at this is summation stuff. But, so, yeah, we're going to have to grind for that. But I think that's what this chapter is about, is integrals and all the beautiful new things we can do with integrals. But the gist of it, in my mind at least, is that the integral is the opposite of the derivative. Now, that's a very specific theorem. That's the fundamental theorem of calculus. But in my mind, that's like the definition of what an integral is that it's the opposite of the derivative. The other cool thing that the integral is it's the area under the curve. But I'm sure we'll ease into that and get into all that soon. But it looks like the first thing they wanted us to see is that the integral is the opposite of the derivative. And when you're trying to calculate it, that's the really important thing to think about.